We're working on homework 2.3, acceleration, and we're going to be doing question 3 right now. Question 3 is broken into two parts, but we're provided with some givens right off the bat. We're talking about a runner at a starting gun. So if we know anything about runners, here's something we need to assume. Our runner starts from rest, from having no velocity at all. So VI is 0 meters per second. That's what the starting gun usually initiates, the run from a rest. And the acceleration rate, is 1.9 meters per second squared, meters per second per second. So every second the runner travels, he or she will be traveling at 1.9 meters per second faster than they previously were. And it says for 5.2 seconds. We're actually going to come back to that in a little bit. Well, I'll write this at the top, that at 5.2 seconds, the runner's acceleration is 0 at that point. So acceleration equals 0 for the rest of the race. Does that mean that the runner stops running? No, it simply means that the acceleration is 0. So no longer is he or she getting faster, but they maintain that constant speed. So that means at 5.2 seconds, the velocity is the same. Velocity is same for the rest of the race. Later on, well, we'll come back to that, but that will be helpful later on. But at A, right here, in question A, or part A of the question, it says, okay, well, when at t equals 2 seconds, so 2 seconds after the starting gun, how fast is our runner moving? 2 seconds, 2.0 seconds. So our final velocity, you can say final velocity A, because this is part A, is, well, we're not sure. Remember that our acceleration is the change in velocity over the change in time. And we can write that as our final velocity minus our initial velocity over the change in time. It is our final velocity that we want to find in part A right here, or VFA. That's what we don't know. So if we were to rearrange that, if we were to, again, this is equal to A, we would bring our t up to the A side by multiplying both sides by delta t. So let's do that. VFA is equal to A times delta t. And then we're going to add VI to both sides to bring it over to the other side of the equal sign. So we're solving for VFA. And that is acceleration. That's VI. So all this equals our acceleration, 1.9 meters per second squared, times time, times how many seconds? In this instance, it's 2 seconds, or 2.0 seconds, plus our initial velocity. Well, that's easy. Our initial velocity is 0 meters per second. So our velocity at A is simply 1.9 times 2, and that's 3.8 meters per second. For part B, it asks us what's the velocity at the end of the race. So delta t is end of the race. Well, we don't know that. But what we do know is that whenever the end of the race is, the velocity is going to be the same as it was up here at 5.2 seconds, because we were told that the acceleration at that point becomes 0, and it's merely the velocity that stays the same. Velocity is the same for the end of the race. So at the end of the race, the velocity is the same as it would be at 5.2 seconds. So we can say that our delta t is now 5.2 seconds. I will try to also provide a little graph that would illustrate what's going on here as well. So what's our acceleration? Acceleration is still the same, 1.9 meters per second squared. Our initial velocity is 0 meters per second. The only thing that changes is the time. So velocity final b is the same as what we have up top right here. That is acceleration times the change in time plus our initial velocity, VFB, and that is 1.9 meters per second squared times now 5.2 seconds, right? 5.2 seconds plus our initial velocity. Hooray, that equals 0 meters per second. So we don't need to worry about adding that. And 1.9 times 5.2, that comes out to 9.9 meters per second. That's our velocity final at B. Box that off right there. So to illustrate this, get a new page here. Hopefully I can help illustrate what's going on here by drawing a simple graph. This is our velocity here, and this is in meters per second. And this is our time in seconds. It's an S right there. And our red line is going to illustrate our acceleration. So let me go back here. Okay, so we have some times to mark here. Let's mark 2 seconds, 2.0 seconds. And right about here is 5.2 seconds. We have an initial velocity of 0 meters per second, right? Because our runner jumps out of running blocks, or starting blocks. And we have an acceleration of 1.9 meters per second. That is, we're told the slope of the line, of the acceleration line. So that's going to be right about that slope right there. So for 5.2 seconds, the runner accelerates at 1.9 meters per second squared. And then the rest of the race, whenever that goes to, the acceleration equals that. Here, the acceleration equals 0 meters per second squared. So what that means is the velocity is going to be constant. The velocity is going to be, velocity is going to be whatever it is right here. So we found out in part A, by knowing our acceleration rate and knowing the time, and knowing that the initial velocity was 0, we found out that our velocity at A is 3.8 meters per second. So this is velocity final A. And we did the same thing with part B. So this is A right here, that's B. We did the same thing. Now the question asked us at the end of the race. Well, we said since the acceleration is 0 after 5.2 seconds, the end of the race speed is the same speed as, or same velocity as right there. So we could use 5.2 seconds to find out, and the acceleration rate to find out what the velocity would be. And we did that. We found out that velocity final of part B is equal to 9.9 meters per second squared.